Going orbital is a crucial part for keeping a spacecraft up in space and for going on any journey to other celestial bodies. In our last video, we talked about how rockets can get to space, but not necessarily how they can stay in space. But what is an orbit anyway? Why is it so crucial to any space mission? And most importantly, how can we design a rocket that can not only reach space, but go orbital? Let's get straight into it. Before we talk about how a rocket can reach a stable orbit, we first need to know what an orbit is. According to NASA, an orbit is a regular, repeating path that one object in space takes around another one. It's essentially when you are constantly circling around an object in space. This could be, for example, a planet or moon. Here's an example from the spaceflight simulation game, Kerbal Space Program. An object that is orbiting another object is called a satellite. As an example, the moon is a satellite of the Earth, and the Earth is a satellite of the Sun. These are called natural satellites. Artificial satellites are satellites built and sent up to orbit by humans. Some examples of artificial satellites are the James Webb Space Telescope, the International Space Station, and the thousands of small Starlink satellites orbiting the Earth. When in orbit, you are basically always falling to the celestial body you are orbiting, but never hitting the ground, but instead circling around again and again. This is very useful as, unless anything slows you down, you will stay in space. Now that we know what an orbit is, we need to know how to get to an orbit. We'll start with orbiting the Earth. The Earth is the largest and most massive rocky planet in our solar system. The more mass an object has, the stronger its gravity. This means that not only do you have to fight against the Earth's gravity to get to space, but you also have to be going fast enough that the Earth's strong gravity can't pull you down to the surface. This requires a ridiculous amount of power, fuel, and thrust to accomplish. So how can a simple rocket overcome the gravity of an entire planet? The answer is speed. Even when you simply jump, you overcome the Earth's gravity for a second and go up before losing your speed and being thrown back down towards the surface due to the Earth's gravity. Since rockets, however, are always gaining momentum, they can continuously go higher and higher until their fuel is depleted. Once in space, the rocket can gain momentum even easier. The reason why is because the further away you are from a celestial body, the weaker its gravity is on you. Meaning, if you are over 100 kilometers above the surface, you can not only fight against the Earth's gravity easier, but you also don't have to worry about any air slowing you down. Once air is not a problem in space, rockets will usually tilt completely horizontally, building up horizontal velocity. Velocity refers to your speed in a direction, such as your vertical speed and horizontal speed relative to another object. Here is a small example in Spaceflight Simulator. You can see my speed going downwards, but also my speed going sideways relative to the moon. I talk more about these concepts in episode 4, How to Get to Space, which you should watch if you haven't already, as this video may make more sense. When you are orbiting around the Earth, gravity still does act on you. Gravity is always acting everywhere, all the time. This is why you go around the Earth instead of being shot out into deep space. However, since your horizontal velocity is so fast, the Earth's gravity isn't strong enough to pull you down enough to hit the ground, but it still is strong enough to pull on you and make you circle the Earth instead. These concepts go the same for any other celestial body in the universe, some requiring more effort than others. Getting into orbit of even the Earth is still no easy task, requiring an absolute minimum of around 8 kilometers a second of delta V if you get there as efficiently as possible. Now that we know how to achieve an orbit, we must know what types of orbits we can take around the Earth so that it is most suitable for our mission. There are many types of orbits that all have their different benefits. The most common type of orbit is called a low Earth orbit, or LEO for short. This is when you are orbiting the Earth at any altitude less than 1,000 kilometers and above 160 kilometers from sea level. This can be from any angle. As this orbit is closer to the surface, it requires less fuel and maneuvering to achieve. This is the main reason this orbit is the most popular. In fact, around 55% of all satellites sit in a low Earth orbit. This orbit is particularly handy for space stations that require orbital construction, as less effort is required to bring up each module, and Earth observation satellites, as they can see our beautiful planet in more detail. Another harder to achieve but still useful orbit is a geostationary Earth orbit, or GEO. A geostationary orbit is when you are orbiting the Earth at the same speed it is rotating. This means you always stay above a certain position. The requirements to achieve this are much harder than LEO. To achieve this, your path and angle around the Earth must be equatorial. In other words, your path around the Earth is the same as that of the equator. To be orbiting at the same speed of the Earth is rotating, you must be at the exact height of 35,786 kilometers. This is substantially higher than a low Earth orbit, and more fuel is needed to achieve this. This orbit is very good for communication satellites, as they can always stay in connection with a large area, and satellite antennas on the ground do not have to rotate to stay in connection. An orbit between the points of geostationary and a low orbit in terms of height is classified as a medium Earth orbit, or MEO for short. The final main type of orbit I'll cover in this video is a polar orbit. This is when your orbital path crosses both the north and south poles of the Earth, or any other celestial body for that matter. A polar orbit does not have anywhere near the strict requirements for a geostationary orbit. Even being 20 to 30 degrees off where the poles are is still classified as a polar orbit. Polar orbits are another great option for Earth observation satellites. If you are directly crossing both of the poles, the entire Earth will pass below you as the Earth rotates over time, meaning you will be able to see every single part of the planet eventually. Clearly, some of these orbits are harder to achieve than others, requiring more speed. The required velocity for LEO is at least 8 km a second. However, the required speed for a GEO, or a geostationary orbit, which is 30 times higher, is around 3 km a second. This doesn't really make much sense at first. After all, I said earlier that a geostationary orbit is much harder to achieve, but why would it be if I have to go over half the speed? As I briefly mentioned earlier, the higher the orbit is around the celestial body, the slower you need to go to orbit it. For example, our planet Earth, part of the inner planets, takes 365 days or 1 year to orbit the Sun. On the other hand, the planet Neptune in the far outer system takes exactly 60,266 days to orbit the Sun. To put those numbers into perspective, that is around 165 years. The last time Neptune was in the position it is today was in 1858. That was 68 years before the first liquid-fueled rocket was invented, and 45 years before the first aeroplane was invented. As I mentioned before, the closer you are to a celestial body, the stronger its gravity. This means that the further away you are, the weaker its pull is on you. If somehow Neptune swapped places with Mercury but was still orbiting at its original speed, the Sun's gravity would easily pull it in, and the Sun would completely swallow Neptune. If Mercury swapped places with Neptune, however, and still maintained its original speed, the Sun's gravity would not be able to hold it in any longer, and it would be ejected into interstellar space. This is because Mercury orbits a lot faster than Neptune, as it is forced to because of the Sun's massive gravity as it is so close to it. On the other hand, Neptune can orbit so slowly as it is so far away from the Sun, therefore the Sun's gravitational pull is a lot weaker. But how does this help us answer our question on geostationary orbits and why they're harder to get to? Getting to a geostationary orbit is still harder, as you first need to accelerate to a velocity of around 8 km a second horizontally relative to the Earth in space to achieve a low Earth orbit. You then need to use even more fuel to raise your highest point, or apogee, to around 35,000 kilometers from your perigee, and burn again at your apogee to create a circular orbit. This is known as the O-Berth effect, which I will discuss in greater detail in episode 6, How to Fly in Space. However, I won't make you wait. Episode 6 should already be out by the time you are watching this video. As you are higher, you are orbiting much slower, but have still used more fuel to get there. But what if I don't want my rocket to just reach orbit, but go to a more distant destination such as the Moon? Which orbit should I first take? The legendary Saturn V, which sent a total of 12 people to the Moon, launched into a low Earth orbit each time. They first entered this orbit before going to the Moon, as it is much more efficient and allowed them to prepare for the journey ahead while still being close to home. Because a low Earth orbit is the easiest to get to, the spacecraft could use the least amount of fuel possible for ascent and orbit and save the most fuel for the Moon. A circular orbit was critical for this mission, as that way they could burn from any position they needed to get to the Moon as efficiently as possible. It was the American aeronautical engineer Robert Anson Heinlein who said, "Once you're in orbit, you're halfway to anywhere." recognizing that reaching an Earth orbit is a very difficult task, requiring a lot of fuel and thrust, and is usually half the challenge, if not more, of any space mission. Once again, much has been discussed in this video, and with this topic, there is a lot to cover. So let's do a quick summary. An orbit is the path around a celestial body that repeats itself and goes around again and again and again. As long as nothing slows you down, you will continue going around that path forever. To reach an orbit, you must first overcome the gravity of the celestial body by first reaching space if it has an atmosphere, and then traveling so fast horizontally that gravity can no longer pull you down to the surface. When in orbit, gravity is still acting on you and you are still falling, but you never hit the ground. When reaching an Earth orbit, you must be traveling at around 8 kilometers a second horizontally in space above the atmosphere. A low Earth orbit is any orbit from less than 1,000 kilometers from sea level. A geostationary orbit is when you are orbiting at the same speed the Earth rotates and orbiting on the same angle as the equator, so that you are always stationary above one spot, which requires a height of around 35,000 kilometers, and a medium Earth orbit is anywhere in between. A polar orbit is when you are orbiting anywhere less than 30 degrees away relative to both the North and South Pole. These orbits are all useful for different missions. The further away you are from a celestial body, the weaker its gravity is on you. This is why the required velocity for a geostationary orbit is only 3 kilometers a second. This is still harder to reach, however, as you have to gain more velocity to reach this height and make your orbit circular. Each orbit is beneficial for specific missions in space. Communication satellites are good in a geostationary Earth orbit, as they are always in connection with a large area. Moon, Mars, or other deep space missions are good in low Earth orbit, as they spend the least amount of fuel ascending and getting to orbit, and can save the most fuel to get to their destination. Space stations that require multiple launches to construct are good for low Earth orbit, as each new module requires less effort to get up to space and dock together. Satellites that provide high-speed internet connections, such as the thousands of SpaceX Starlink satellites, are most suited for low Earth orbit, as they are closer to the surface and can connect extremely quickly with the Earth. And satellites and probes that want to observe the Earth, or certain parts of it, and observe how they change over time, are most suited for a polar orbit, as eventually, the entire planet will pass below you as you orbit and the planet rotates. Orbits come in many different forms, but have allowed us to stay in space while using the least amount of fuel possible, leading to incredible spacecraft such as the International Space Station, where astronauts can live and work in space for around 6 months at a time, something that would not be possible without achieving an orbit. While getting into orbit is by far not the most exciting part of incredible space missions that push the boundaries of what's possible, it is absolutely crucial to any space mission that wishes to travel beyond the known world and venture out and discover our incredible universe beyond.